stick to the middle board. I will begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I just ask you to help us to use this time wisely, just to work on whatever it is we don't understand, Lord. In your name I pray. Amen. Do you guys have a question? Direct sums. Yes, sure. I remember my thought. I can, of course, go through the solution to like the previous test if that's helpful. Would that be a good thing to do in here? That might be a good thing to do. But before we do that, we can talk about direct sums. So what is a direct sum? Is your question? Yeah?
I think we like the application of it.
Application of it.
Like, I think it gives the definition.
Mm-hmm. So for two things, yeah, go on. Just what is it? Was it for? Well, one of the things it's for is we're currently studying linear transformations, right? So if you can write V as, say, E1 direct sum, E2 direct sum, say, out to K of them, and suppose these are the eigenvectors with eigenvalue lambda 1, eigenvalue lambda 2, eigenvalue lambda k. So if this is the case, that means that you have enough eigenvectors to fill out the whole space. So it would say that there's an eigenbasis for T. And so, you can pick an eigenbasis for T, something like V1, let's say V11, V1 M1, V2 1, V2 M2, and so forth and so on. Eventually you get to the kth one, and however many of those you need. So like this would itself be a basis for E1. These vectors would span, form a basis for the kth eigenspace. I'm assuming that lambda 1 through lambda k are distinct. So if you had this set up, it's interesting because if you make your whole basis a concatenation of like the basis for each eigenspace, put them together like this, and then you look at the matrix for T. The matrix for T with respect to choice of basis like this, what it's going to look like is like lambda 1, lambda 1, lambda 1, and then lambda 2, lambda 2, and so forth and so on. Eventually I get to the kth one like that, where you've got as many, so there'd be like M1 of these, M2 of those, MK of those, something like that. So that's one of the reasons direct sums are interesting, is if I can find subspaces which are direct sums, that means I can maybe find bases which respect that and make the linear transformation have like a nice special formula. The larger story here is if you can find direct sums, you can focus your attention on a piece of the linear transformation rather than it as a whole. I mean, if you have a direct sum and you have this, then that means that you can define this thing, which is I would say it's just the restriction of the linear transformation to W1, but it's more than that. You're taking like the domain for T is all of V, right? The codomain is all of V as well. So here I'm restricting the domain to W1, and I'm replacing the codomain with W1 as well. So this is a related but different linear transformation to T, which just focuses on what the linear transformation does to the subspace W. And it's the case for, like we proved today, that eigenspaces were invariant. we're T invariant. So this happens for eigenspaces. And so like more generically, if you have all of these, if these are all invariant subspaces and you're looking at the direct sum being like that, then that means that you can form the matrix of T with respect to the appropriately constructed basis to just look like A1, A2, AK, where these are, it's a block diagonal matrix. If you like, we could say A1, direct sum A2, direct sum AK, where, you know, this, like A1 would be the matrix of T with respect to the, so, you know, you asked me, what are direct sums good for? That's not something I can answer quickly. That's like it's a big idea, and it's all of this together that makes it interesting. Is that we can find a block diagonal form. Mm-hmm. It could be. It depends on whether or not is it a Jordan form. The question was whether or not this is a Jordan form. This would be a Jordan form if the A's were Jordan blocks. This is a Jordan form because a diagonal matrix is a special and most easy case of a Jordan form. Yeah? So, yeah, if we can find a direct sum decomposition of the vector space such that the independent subspace which form the sum are each invariant with respect to the linear transformation, then that allows me to make the matrix, like find a basis which makes the linear transformation like a really nice special form. Yeah. And since generalized eigenspaces and eigenspaces are exactly those kind of invariant subspaces, that's why these ideas work together for, yeah. Okay, so let me see now whether or not, oh, it worked. Small miracle. This room is very hit or miss. It's okay, I just told them what's on the final. Oh, really?
Yeah. She was like really sad. We're like, we're not going to be in class. And she goes, oh, why?
Aww.
Yeah, like I'm feeling later. She goes, you know, you got to prioritize. Yes.
Well,
She said that to me.
but again, I don't think it's a good for a continual pattern.
Yeah. We decided we might start rotating.
Well, next Wednesday will be assessment day, so don't worry.
That's the perfect time to have another review session. Review. No, like serious. Exactly. I'm very serious. I would definitely stay here for like 3 hours.
All right, so I was just saying that I will go through the solution to test 2 because that's something pretty much everybody needs to see. And, you know, maybe it helps, perhaps it helps to see me actually talk through it. I don't know. Anyway, I'm going to do it. So, oh, it's okay. I mean, I'll tell you if I do. At the moment, it's fine. So, let's start with the first problem. So here I gave you a basis of 3 vectors, right? And I told you that I'm thinking of it as a subset of R7, all right? I told you the coordinates of a particular vector are 4, -1, and 1 here. And then I said calculate V. So how do you work this problem? So a lot of you, like 70% of the class, did some kind of matrix multiplication here. I think what that is you're misinterpreting my advice to calculate coordinates. See, calculation of coordinates requires, I mean, this is just the definition, right? Remember, what was their definition? Given beta is v1, v2, vn, then what? X equals to x1 v1 plus x2 v2 plus xn vn if and only if the coordinate vector of x with respect to the beta basis is equal to x1, x2, xn. So I guess I used a v instead of an x here, but I hope you can see the pattern. The point is, I know I look at this and I go, so if that's the coordinate vector, to build the vector, I take the corresponding linear combination of the basis, right? There's nothing to calculate here. You just have to do it. Well, there's something to calculate, this, right? But I'm sorry, in my book, that's not really a calculation, right? Like, calculation is something that requires, like, more thinking. So anyway, any questions? Does that make sense now that see, I think everybody in the class could have got this one, right? No, nobody should have missed this one. I'm going to be saying that a lot today. Now, I will say this. I think, I'm not 100% sure, but I think pretty much everybody got this one. So, good news. You guys, I think, if you're here and you got it wrong, don't tell me. Like, let me labor in my delusion that everyone got this right. I prefer to live in that delusion. So there's that one. All right. Now, let me point something out here. If we go to the linear notes, all right, let's search sum of subspace maybe. Did I ever write that? No matches found. Let's see here. How many instances of sum? Oh, you cursed double browsing fast finger thing. So annoying. Where did I? So I wanted to show you guys. I think it's back in chapter 6 when we were first talking about subspaces. Actually, a little bit after we first started talking about the subspaces. Somewhere, I believe, talking about, come on, where'd you go? I should have told you guys to take your Dramamine. Oh, there it is. So, you know, ever since Math 200, you guys are all excited about unions and intersections, right? Yeah. So a natural question to ask yourself whenever you're working in mathematics is the intersection of two things a thing? Is the union of two things a thing? And so, yeah, the intersection of two subspaces is a subspace, right? On the other hand, the union of two things, let's see, do I say it in here? On the other hand, all right, come on. I said, intersection to the sum. What is wrong with me? Have I written the wrong word? Oh, yeah, there it is. I feel like... Oh, this is also true. We do have a theorem which relates the intersection to the sum. What was that theorem? which one am I referencing? I'm talking about this theorem. The dimension of W1 plus W2 is dimension W1 plus dimension W2 minus the dimension of the intersection. That is, I did not prove that for you guys. That's a little bit involved. It takes me about a half hour to prove that one. But the proof is in the notes. I think it's theorem 6.78. But yeah, right here. If you consider the union of two subspaces, you'll find the result's only a subspace when one of the subspaces contains the other. For example, the union of the x and y axes in R2 is missing sums such as this. If we take this is on the x-axis, that's on the y-axis, this is on the union, this is not in either one of them, right? So union of two subspaces very rarely is actually a subspace. And that's what this problem was on the test, all right? Now, maybe you didn't look at it like that, but I was hoping that some of you would have looked at it that way, you know? But very, very few of you got this. Like, so many of you fell for my trap, which was, I thought a lot of you would just say, oh, it's a span, so it's a subspace, right? But it's not actually a span, it's a union of two spans. Right. And I think that's why you guys got it wrong, is because you have to be careful. You know, a union of two things isn't necessarily a thing. Well, now you know. All right. Any questions about this one? So, and to prove that, you just need to, pick 2 points in W, like this one and this one. And if you add them together, you get 2, 1, which is not in W. How do I know it's not in W? Because 2, 1 is not in here, and it's not in there. And that's what it takes for something not to be in union. You have to prove that it's in neither one, right? So I think there were like 2 of you who got this right. That may be an overestimate. Problem 4. Problem 4 actually requires some calculation. All right. So the question here was to find a condition on A, B, and C such that that set forms a basis for P2. So we need what? We need that those vectors are a spanning set for P2, right? Or we could prove that they're linearly independent for P2. I mean, you got that's your kind of your choice. I decided that the easiest way to answer this question would be to look at the coordinate vectors for these with respect to the usual monomial basis, right? Because we have a theorem that says I can test linear independence of a subset of P2 by looking at the corresponding set of coordinate vectors for the vectors, right? Remember we had that the coordinate map is an isomorphism, and isomorphism preserves linear independence. So linear independence or lack thereof for this is going to tell me about the linear independence or lack thereof for that. But I prefer this to that because this is a set of three-dimensional column vectors, right? In particular, the coordinate vector of ax squared plus bx plus c is abc. The coordinate vector of x plus 1 is that. The coordinate vector of x squared plus 1 is that. And so to get linear independence of the columns, that's tantamount to saying that that matrix is invertible, right? And to my taste, the easiest way to check on that is to calculate the determinant. Does that make sense? Now, there's other ways you could have gone about it, right? What would have been another way to try to solve this? If you didn't think of my trick, how would you do it? I would have suggested you do this. You do something like, C1 times ax squared plus bx plus c. So could you, yeah, thanks. C1 times ax squared plus bx, oh, I can't say anything today, plus C2 times what? X plus 1, right? Plus C3 times what? X squared plus 1. I would take that, I would set that equal to 0, and I would see, assuming that that linear combination is equal to 0 gives me only the trivial solution. I try to understand what that means, So if you look at that, we've got x squared times c1a plus c3, right? And we've got x times c1b plus c2. And then the constant terms, we've got c1c plus c2 plus c3, right? All of that's equal to 0. So looking at using linear independence of the monomial basis, which we know, we get that the coefficients of x squared x and the constant term have to separately vanish, which tell me, like, for example, c1a plus c3 equal to 0. And c1b plus c2 has to be equal to 0. And also c1 plus c2 plus c3 has to be equal to 0. Translating that, we're looking at this following problem. A, 0, 1, B, 1, 0, C, 1, 1, times the column vector C1, C2, C3 equals to 0. I want there only to be the 0 solution here. So again, I'm driven back to seeing that I need the determinant of that matrix to be non-zero. This would have been another, completely logical way to solve problem 4, right? And when you calculate the determinant of that matrix, we get a plus b minus c not equal to 0. Now, some people got maybe half credit here for finding me an example, right? But I think it's clear from the wording here that I'm looking for a condition. So what I mean by an example is basically some people were like, well, put a equals to 2, or no, maybe put a equals to 1, b equals to 1, and c equals to minus 2. That works. Oh, wait a minute, that won't work. I think put a and b and c all equal to 1, that gives you non-zero, right? So for example, if you put x squared plus x plus 1 into the first entry, that gives you a basis, right? But I'm not here. This question doesn't intend for you to give me one example. I want to know a condition on ABC which will characterize all possible choices for that to be a basis. If that makes sense. Now, if you were confused about the wording on that point, I would be happy to clarify it during the test if you asked me about it. That's a completely reasonable question to ask. Are you looking for one answer here or many? I'll at least give you an answer or some kind of cagey non-answer, which would be in some way helpful or annoying. But I try to be helpful. I also try to be annoying. I feel like it's my responsibility, but in a good way. Problem 5. Any questions about this? You can always interrupt in here. Yeah. Yep. Okay, so I think I know what happened without going over there. So you had this equal to 0 up here, right? So we shouldn't write that. I mean,
I think I did it because of the condition.
right. Let's see here if I can give a non-linear algebra example of this kind of proof writing. And you were taught it in high school, probably. All right, so here's see if I can think of something. So tangent squared theta plus 1 equals to secant squared theta, right? So that's a question mark, right? And then try to think of how. good example? Yeah, sorry, coming up with examples. So I'm trying to come up with an example of something that's wrong, which is for some reason very challenging for me. I mean, I've been coming up with things that are wrong all today, they're not as examples to serve a point. So, how can I say this? I should look at your. I guess I should just not fight. I should just go with this, right? Why come up with another example when this will do? Well, I mean, I'm trying to come up with some analogy which sheds light on why this is wrong, but, you know, this. Thank you. And then, of course, what she does is then proceeds to make steps, right? So then she's like C A transpose plus B transpose plus 2CA plus 2B equals to 0, and then CA transpose plus 2A plus B transpose plus 2B equals to 0. So then C times 0 plus 0 is equal to 0. So then 0 is equal to 0. And so this is what I would commonly refer to as a 0 equals 0 proof. This is not how we write proofs in mathematics, though. Right? I mean, because this is what you're trying to show. So it's bad form. Our goal is to show this. So what you should do is start with what you're trying to show is 0, right? And then apply properties and results which you know to manipulate that to make it be 0. To the casual observer, it looks like you're assuming the point here at the start. Now, I agree that like all of the ingredients here, like all of the necessary ingredients for the correct proof are here, but they're out of order is the thing, right? Like the logical flow is like that, you know? Be like, well, you know what I was, you knew that I knew what I was doing. That's why I didn't take off that much, right? Yeah. But I do think it's something we need to try to fix, right? Because this is not, and I think it's really, I know that this is not uncommon. Like I was trying to come up with a trigonometry proof. This is not uncommon for trigonometry proofs to go like that, right? Something like, I was trying to do something like tangent squared theta, plus 1 equals to secant squared theta. So, cosine squared theta times tangent squared theta plus 1 is equal to cosine squared theta times secant squared theta. So sine squared theta plus cosine squared theta is equal to 1. So 1 equals to 1. So like this is a kind of proof style that you've been exposed to before. But it's poor without extra writing, right? Like there's a way to repair this. Something like for cosine of theta not equal to 0, context, this, if and only if this, if and only if this, if and only if this. And then a concluding sentence would be nice. Since 1 equals to 1, tangent squared plus 1 is equal to secant squared theta. I still don't like it as a proof, though, right? I much prefer to start here, assume that cosine squared is not equal to 0, right? So divide by cosine squared and, go like that way of doing it. Oh, wait a minute, I'm an idiot. Why am I writing this? So, I mean, this would be kind of, start with the thing that's true and is known for other reasons at this point in the course, and then you make allowed steps on it to derive the thing which is true. You don't begin with the thing that is true and you're trying to prove and manipulate it, because it looks like you're assuming the point. Yeah. I try to be more, I try not to think the worst of students, right? So like, you got to beware. I mean, if you come across a grumpy professor on a wrong day, they see the 0 equals 0 kind of proof, they're not even going to look at it. They're just going to be like, 0. But I try not to do that. So anyway, any questions? But I appreciate your question about that, because it's one of the things I want to talk about. Thanks. Let's see here. Part A, you notice I made the non-bonus part worth the most, and like to get these 10 points, all you had to do was to look at this and go, oh, that's the span of 1 plus x squared and x. Span is subspace. 10 points. See? Everyone here could have had those 10 points. Like I said, that's going to be a theme for today. So I'm sorry, but now part B is, that required a little bit of sneakiness. I'll tell you what I did here. Is I basically, to give you an outline of what I'm doing, I'm taking the subspace and rewriting it as a set of equations. And then I'm using those equations to inform my formula, because the formula being 0 would mean the equations hold, which would mean that the kernel is the subspace in question. So I said, okay, I got C1 plus C2x plus C3x squared equals to the span. The question is, what conditions on C1 and C2 and C3 do I need to make it have this form? I need C1 equals to A, C2 equals to A plus B, C3 equals to A. My goal is to eliminate A and B to find equations for C1, C2, and C3. So it's easy enough to do. C1 equals to C3, right? And C2 is equal to C1 plus C3. These two equations and those three unknowns describe the subspace. This is a trick you guys saw in the homework before for the intersection problem. Remember? Uh-oh. Because C1 is equal to A and C3 is equal to A? No! Did I do that? Ah. Oh, man. Son of a motherless goat. Why did I agree to go over this solution? Now I got to fix it. Blast it. How can I fix that? Meh. Well, so here's what this is. I mean, this is actually a much nastier in some sense, but it's good that this has come up in the discussion. So this is in no way related to C1 or C3. So that means that B can range over whatever it wants, right? In other words, C2 is free. So basically, this doesn't tell you anything. And the only equation is just C1 equals to C3. The second equation's out. I don't even need it. And so I could have just blank this out. Just blank that out and just say that C1 plus C2x plus C3x squared is equal to C1 minus C3. That would have been enough. That would work, because then the kernel would just be the set of polynomials such that the constant and the x squared term are the same. So, and that gives you, this W is the span of 1 plus x squared and x, which I think is what I started with, right? Oh no, 1 plus x squared and x, but yeah. All right, well, I'll try to fix this and write it out, okay? Let's move along here. Nothing to see here? This one. Any questions? I think most of you realized that you probably need to do the row reduction here. And a lot of you tried to do something, and then I think at this point, test-induced depression and or dementia come into play, and your inability to row reduce was altered. But you can do row reduction, I'm quite sure of it. And if you do, you get this. And doing, yep.
Is it necessary to move the 1 and the 3 halves from row 3 to row 2? Because I didn't, and I got A right. I probably got B right for an unrelated reason.
Oh yeah.
Or wrong, I mean.
Oh, I mean that's a fair question.
Could it still be? Could it just be E1
I
and E3 instead of E1, E2?
I honestly, I think you could stop right here. I think here it's already clear what's going to happen, that columns 1, 3, and 5 are the only non-zero columns. Well, anyway, it's going to be clear that columns 1 and columns 3 are working out to the pivots. Right, and so eventually there'll be standard basis elements. And it's also clear enough, even from here, that the fifth column is built from what? It's built from, you can probably figure out how to build the fifth column from the sum of the first and the third if you stare at it hard enough, but eventually you'll learn that 3 halves the third column minus 1 half the first column gives us the fifth column. So, I mean, that information wasn't actually mission critical to this problem, so yeah, I mean, fair enough. You could have stopped right there and probably had all the information you needed to answer the question. It's true.
Okay.
It's true. But I know this. Once I find the reduced echelon form, I know, I'm just doing that because I know for sure that all of you should remember that the pivot columns form the basis, not these pivot columns, but the original columns, the pivots form the basis for the column space, right? And but the good thing about I should comment, the good thing about getting to this point, or getting to the point you got to,
Yeah, I was just one step
is that the null space, I mean, if you stop here, you might get confused about the role of the free parameters in the null space. It kind of depends on how Like if people don't reduce the equations enough when you go to trying to find the null space basis, you can trick yourself into thinking you have more than you do. Of course, there's a simple antidote to that, which is rank nullity says that the rank plus the nullity has to be 5 here. 3, a very popular wrong choice. I don't know. People said rank plus nullity equals 3. I'd assume it's because there's 3. But it's the dimension of the domain, which here is our 5. If we look at the linear transformation Elsevier, if you like. Anyway, get to it here. So yeah, a basis for the column space is the first and the third. I suppose you could have used the first and the fifth if you wanted. Yeah. Also would have been legit, but that's my preferred choice. Once I see that there are 2 things in here, that tells me the rank is 2. And then to find the basis for the null space, I have to sort through the solution AX equal to 0. Having already calculated the reducer echelon form, I know x1 is 1/2 x5 and x3 is minus 3/2 x5. So x is, here's my x1, x2 is whatever it is. Here's my x3, oh man, I'm sorry, when I go back and fix this, I was going to white that out. Right, that's still, yeah, it doesn't work. X4 and x5. So as predicted, 5 minus 2 is equal to 3. 3 is the nullity here, the number of free parameters in the homogeneous solution. X2, x4, and x5. And whatever appears here, here, and here, there's your basis for the null space, or the kernel of T. Anyway, the nullity is 3. Now, part C was based on what homework question? We were mission 6 right before? You're like, let's look at mission 7 solution then. Let's see here. This is part 2 or what? Now, I need to look at part 1, don't I? Okay, so this is like problem 93. Curses. Problem 93, I was actually using my notes. Well, fine. My solution on the test basically follows the proof of the rank nullity theorem that we did. Let me go back. Where did I put it? I got too many things open. All right. So the question was to figure out what, or just, I mean, I didn't say you had to, I said, I don't think I said find all possible choices here. I was actually content if you would find a choice which made this happen. All right. I really don't want to grade all possible choices here. It's just a mess because there's a lot of answers. But whatever you do, you're looking for a basis that makes this the matrix of the transformation. So that means that I want to put the part of the basis which is forming the null space or the kernel, I want to put that last, right? So we know that E2, E4, and this guy, all right, or you could, yeah, right here, right? This is the basis for the null space. So I put that last. Okay? And then whatever I put at the start, it has to map to something non-zero. If it maps to 0, we're in trouble because then we can't take 0 and turn it into a coordinate vector which is non-zero. So like what's informing everything I'm doing here is, whoa, that the the matrix of T beta gamma, what's it look like? It's T of the first thing, and then T of the second vector in the basis beta with the gamma coordinates of that, T of the fifth, right, and I'm not looking at the notation in the problem right now, so if I'm misusing what V has already been used as, my apologies. I'll slap some tildes on it shortly. Okay, I didn't use V. We're good. But the point is, whatever my choice is for V1 through V5 for my basis beta, it has to make zeros in the last 3 columns, right? So I should use the kernel basis for that. And it has to make the first 2 to be non-zero, right? If I put 0, if T of V1 or T of V2 is 0, that doesn't work, right? And I forced you guys in the problem statement to select the first 2 things from the standard basis, right? So EI and EJ has to be standard basis. How can you be sure that T of EI or T of EJ is not equal to 0? What is T of EI? It's the ith column, right? What is T of EJ? It's the jth column. So if you go back to, if you go back up to here, really, the only thing you can't use for the first 2 parts are the E2 or the E4. But by the way, you've already used those for the null space basis anyway, so you probably shouldn't use them twice in the basis anyway, right? That's definitely linearly dependent. So really your choices are E1, E3, or E5 for the first 2 things in beta. And you can choose any pair of those, as long as you don't use the same one. So that's what I say here. You can use EIJ for any I and J selected from 1, 3, and 5. You could do 1, 3, you could do 1, 5, you could make it 3, 1, or you could make it 3, 5. You could make it, I mean, a lot of different bases are ordered, right? So different orderings would give you different bases. There's a lot of different bases. Great. Then gamma, what you want to let gamma be is T of EI, T of EJ. Doing that makes the coordinate vector for T of EI just 1, 0, 0. So basically, for example, if I choose 1 and 3, then I want to make my gamma to be the first column of T, first column of A, the third column of A, and then to put something, whatever goes over here, whatever I put over here has to be something that's not already in the span of these guys. All right? And I think, again, I forced you to use standard bases, right? So that I wouldn't be, that just makes my grading much simpler. And the one thing you can't use here is E3, which many of you picked. So many of you picked. So many of you picked E3 there. I don't know why. It's unfortunate. I mean, it's just unlucky, but you picked E3. You could use also, you could have put 0, 1, 0 here. That would also work. But the one thing you can't put here is 0, 0, 1. The reason you can't do that is you take the difference of this and that, you get 2E3, right? How would you check if your choice here is a legit choice? If you want this to be a basis for R3, what's a quick way to check that your choice is a reasonable one? I need linear independence, right? What's the easiest way to check if that's actually linearly independent is if the matrix corresponding to that basis is invertible, right? We can calculate the determinant. So if you calculate the determinant of just, put these in a 3 by 3 matrix, the determinant of this is, 8 minus 4 times 1 plus or minus something like that. Anyway, you can calculate the determinant of that and get it as non-zero. That's how I thought through it. So I said part of this test was not easy. The part I was talking about is this part. I don't think this is easy. This is in a wholly different category. Getting this wrong is an entirely different category than getting problem 1 wrong, right? Entirely different category. I think a lot of you got this one, right? Any questions? Or at least the start of it. No? You don't know what you did? Well, let me just run through it. Whatever this matrix is, this matrix times the coordinate vector of A should give me the coordinate vector of the output. So since the output is this, when we multiply this and that, now if you multiply these matrices wrong, that'll mess it up for you. But if you multiply these, you get that. And with respect to my gamma basis, which is the usual lexicographically ordered 2 by 2 matrix basis, this has coordinate this, then that, then that, then that, right? On the other hand, the coordinate vector for A is also A, B, C, D, right? Like that. This is that, right? I didn't write that over here. I usually do that. I don't know why I didn't write that there. And then I can just fill in the blank, right? So if you look at this, to get A plus 2C, I do 1, 0, 2, 0. To get the B plus 2D, I do 0, 1, 0, 2, 3, 0, 4, 0. You can check that it works, right? So if you did get this wrong, you can get it right next time I ask it, right? I mean, or ask something like it. Now, part B was the question, is T onto, is T injective? If possible, find the formula for T inverse. So here, T is a mapping from a vector space to itself. That means we're in the context of that theorem where there's an equivalence between T being an isomorphism, T being 1-to-1, and T being onto. It's 1-to-1 if and only if it's onto, if and only if it's an isomorphism, which is to say if and only if the inverse exists as well. That is, don't take that out of context. I mean, this theorem is only for when the mapping is going from a vector space to itself, right? If these are not the same, then there's no equivalence between 1-to-1 and onto. But in this case, there is. But I personally found it easier here just to write down the formula for the inverse. And so what I did, if I want to find the inverse to a map, I write down the formula for it, like this, and then I solve for the input. Here A is the input, so I solve for A. That gives me A is equal to B inverse times Y. That shows me that T inverse of Y is equal to B inverse Y. Did you guys ever learn this in pre-calculus? So, for some reason, well, I know the reason, I just don't respect it. You're taught to switch X and Y. Right? If you want to find the inverse formula, suppose you're looking at f of x equal to, 1 over 1 minus x, let's say. And you want to find f inverse of x. What are you taught to do? Right, yeah. So let's look what happens if you don't do that. Instead of switching x and y, solve for x. Well, 1 minus 1 over y, right? When you do that, whatever you're looking at is f inverse of y. I prefer this to switching x and y because x and y may not be allowed to take the same values, right? Like if your function in principle, like just dispose from this example for a second, if you're going from a to b, right? If this is x and this is y, and your function goes like that, your inverse function goes like this. So I think it makes sense to have x as the variable for the domain, but y as the variable for the codomain. But the reason that you don't do this in pre-calculus is because we don't think students can think about functions of anything except for x. So we have to switch the x and y. It's especially important to distinguish the codomain and the domain and the codomain variable in an application. Like if A is temperature Fahrenheit and B is temperature Celsius, using x for both will confuse you. Anyway, this is invertible. There's its formula. And if a mapping's invertible, that means it's both one-to-one and onto. So there you go. Now, of course, you could, no, this is just a fun calculation. You can actually calculate the inverse of the 4x4 matrix we just found by calculating the matrix of the inverse. To find the matrix of the inverse, you could use the 2x2 formula, like so, right? And then there you go. That's the inverse, the matrix of the inverse linear transformation. This was not part of the test, right? I was just messing around. So that's a question which was almost on the test to find the inverse of the 4x4 matrix, but I just thought there was enough else going on that I needed to also ask that because you guys were probably going to be overwhelmed with what I'd already done. Yep.
Just making sure that I know what's going on with this. When the inverse exists, it's always one-to-one and onto. And
Yeah.
always onto.
Right.
Okay. If it's one-to-one and onto, then the inverse exists, or is that?
Yeah.
Okay.
If it's one-to-one and onto, then the inverse exists. Yeah.
Okay.
Yeah. If it was just onto, then it depends on the context, right? Like, if it's onto and you also know that the size, quote unquote, I'm using size in a somewhat fuzzy way. Well, anyway, let me stop there. Here is the one I was grumbling about. Yeah. So kernel of t 0, right? Pick x and y in the vector space. Suppose their outputs are equal. What is the definition of one-to-one? It says that if the outputs are equal, the inputs must be equal, right? So if that's equal, take the difference, use linearity. That tells you that t of x minus y is equal to 0. That means that x minus y is in the kernel of t, but that's 0. So that means x minus y is equal to 0. So x equals to y, which proves t is one-to-one. So, yeah. Sorry about that one. Problem 10. So basically, I just said, okay, well, I take that and I write it as this linear combination where these are real parameters. So that shows me that that's a linearly independent set, and there's its basis. Yes, it was shocking to me that about 5 to 10 people got this right. Because you guys got things which were much simpler wrong. So anyway, that is a basis, and so sort of once you see that, then you know what to do. You just A, B, C, D.